Welcome to the debate. For centuries, medicine has acted a lot like a city waiting for a water pipe to burst before fixing it. We wait for the flood, we wait for the street to cave in, and then we scramble to patch the exact spot that ruptured.
Right, it's highly visible, it's dramatic.
And it is inherently always one step behind the actual problem. Today, however, the integration of artificial intelligence into healthcare has handed us two radically different ways to fix the plumbing of human health.
And thankfully, neither of them involve waiting for the street to flood.
Precisely. We now have the tools to completely rewrite medical reality. On one hand, we could theoretically map the entire biological water system at a molecular level. We could predict exactly where and why a failure will happen years before a single symptom appears.
Or you acknowledge the reality that pipes are already bursting everywhere, every single day. So instead, you build a hypervigilant, automated global surveillance system, one that instantly detects a microfracture the millisecond it happens, deploying an emergency intervention with absolute precision.
Which brings us to our central disagreement today. Does the true revolutionary power of AI in healthcare lie in decoding the hyper-complex, personalized ecosystem of the gut microbiome to predict and prevent disease?
Or does it lie in automating and democratizing broad clinical diagnostics to eliminate human error on a global scale?
Right. I will argue that transformative AI's greatest potential is in mapping our personal microbial ecosystems to create proactive, predictive health blueprints.
And I will argue that AI's true value is in immediately scaling diagnostic accuracy and accessibility to intercept acute and chronic conditions, basically systematically removing human fallibility from the equation where it matters most.
Let me lay out the foundation for why the microbiome is, frankly, the ultimate medical frontier. Your gut isn't just a digestive tube. It is teeming with an invisible universe.
A very crowded universe.
Extremely. We are talking about roughly 100 trillion microbes, predominantly phyla like Firmicutes and Bacteroides, that actually outnumber your own human cells. This ecosystem dictates almost everything about you.
From digestion to, mental health?
Exactly. It controls how you synthesize vitamins, it regulates your baseline mood, it influences your obesity risk, and it trains your immune responses. For decades, this inner cosmos defied manual decoding because the sheer volume of variables was just impossible for a human mind to track.
Right, it's too much data.
Way too much. But transformative AI, or TAI, has shattered that barrier. We are fundamentally shifting medicine from reactive treatments to bespoke, predictive blueprints. Because we can finally map this ecosystem in hours rather than years, we can preempt diseases before they ever manifest in the body.
The promise of the microbiome is undeniably fascinating, I'll give you that. But we have to look at where the bleeding edge of AI actually meets the reality of human suffering.
Okay.
Broad diagnostic AI addresses a crisis that is far more urgent, highly quantifiable, and happening right this second. And that is the fundamental fallibility of human clinical observation. Medicine traditionally hinges on human senses, right?
Sure, observing symptoms.
Exactly. It relies on a doctor looking at a rash or a radiologist squinting at shadows on CT slices at 2 in the morning. And humans, no matter how highly trained, get tired, they get distracted.
Well, we aren't machines.
Precisely. And this traditional approach results in up to 12 million misdiagnoses every single year in the US alone. By deploying convolutional neural networks and recurrent neural networks to detect conditions like pneumonia, malaria, and atrial fibrillation, we are offering immediate, scalable interventions. We are saving lives today, significantly outpacing the still developing science of the microbiome.
Let's actually dig into the nature of the data and the specific problems these AI systems are solving, because I think that highlights the true power of TAI in the microbiome space.
Let's hear it.
The sheer complexity we are dealing with is staggering. When we use next-generation sequencing on a single fecal swab, we generate gigabases of DNA reads, but that data is incredibly noisy.
Noisy in what sense?
It's warped by what you ate for lunch, whether you took antibiotics a month ago, and even the geography of where you live. Deciphering this is like trying to map the Amazon rainforest molecule by molecule, while the weather changes every 5 minutes.
Wow. Okay.
Traditional bioinformatics completely buckled under this variability. But this is exactly where TI thrives. We use autoencoders to pre-process this noisy data.
Hold on, before we lose the audience in the data science, when you say autoencoders, you're essentially talking about an AI that learns to ignore the static, right? Compressing the data down to its most essential patterns so it filters out the noise of yesterday's lunch to find the actual underlying baseline microbiome.
Exactly that. It systematically strips away the environmental static so we can accurately cluster what we call operational taxonomic units, basically identifying who is actually living in the gut. But it doesn't stop there. Then we apply graph neural networks, or GNNs, to model the interactions.
Meaning the interactions between the bacteria themselves, not just a census of who is there, but who is talking to who.
Or who is fighting who. The AI doesn't just count the bacteria, it maps the relationships. For instance, a GNN can physically model how a specific strain of bacteria, like Akkermansia muciniphila, actively quenches inflammation in the gut by mathematically outcompeting inflammatory pathogens for resources.
So it's modeling a microscopic turf war.
Yes, and because these models are trained on mega atlases, fusing the Human Microbiome Project's American profiles with Japan's MetaHit and Brazil's 1000 Genomes Project, TAI achieves a 98% taxonomic resolution. We can pinpoint incredibly rare, critical pathogens or beneficial species down to the exact strain. You simply cannot process that level of interconnected biological warfare without advanced AI.
I come at it from a different way. That level of complexity is an intellectual marvel, I will give you that. But in clinical reality, complexity is secondary to the volume and the reliability of data interpretation.
Secondary? How can it be secondary if it dictates our baseline health?
Because you mentioned the noise of the microbiome, I would argue that the most dangerous noise in medicine today is human fatigue. Think about that radiologist I mentioned earlier. After reading 100 chest x-rays in a single 12-hour shift, their visual cortex is literally fatigued.
Right. Visual drop-off is a known issue. Exactly. They will look right past the faint ground glass opacities that indicate early-stage pneumonia. Convolutional neural networks, CNNs, don't get tired. And the way they work isn't just by comparing pictures. They extract hierarchical features from exascale datasets. First, they learn to see edges, then they learn to see shapes, and finally, they learn to identify the exact texture of a tumor.
But let me challenge that. Is that process actually fundamentally advancing how we understand human health, or is it just replacing a repetitive human task with a faster calculator?
It is fundamentally advancing survival rates through sheer scale, which quite frankly changes the paradigm of public health. Take InfraVision's AI, for example. It is currently operating seamlessly, triaging 10 million monthly CT scans in Chinese hospitals.
10 million a month, yes. And it operates 40% faster than human workflows. It doesn't replace the doctor. It acts as a hypervigilant filter, immediately pulling the highest risk scans to the top of the pile for oncologists to review. When you are dealing with lung nodules, which are the harbingers of 1.8 million deaths globally every year, the sheer scale of diagnostic AI is its most powerful feature. It is a mathematical certainty applied to a massive population.
I see why you think that, but let me give you a different perspective on when these interventions should actually happen. You were talking about triaging lung nodules and pneumonia.
Which are life-threatening.
True, but those are conditions that have already physically manifested. The structural damage to the pipe has already occurred. TAI applied to the microbiome moves us entirely upstream into predictive symbiosis.
Upstream how?
We are no longer waiting for the anatomical damage to appear on a CT scan. Consider something like irritable bowel syndrome, which torments 12% of the global population. TAI uses LSTM networks, long short-term memory networks, which are specifically architected to understand sequences over time.
And what sequential data is an LSTM analyzing for a condition like IBS?
It analyzes the volatilum, specifically breath gas trends.
So literally, the gases a patient exhales.
Yes, LSTMs are designed with a sort of mathematical memory for sequences. So instead of just looking at a single breath test as a static snapshot, it's looking at a continuous movie of your breath gases over weeks.
Interesting.
It catches the subtle, rising trend of methane and hydrogen, that correlates to a specific bacterial bloom in the gut. By finding these hidden temporal patterns, the AI forecasts an IBS flare days before the patient's stomach actually starts to hurt, alerting them via a smartphone app.
And does that actually improve clinical outcomes?
Absolutely. A recent randomized controlled trial in Mumbai proved that this upstream prediction cut IBS symptoms by 35%. And this predictive power extends far beyond digestion. It goes right to the brain. By fusing metagenomic sequencing with simple wearable data, like a Fitbit sleep tracking, TAI is predicting severe mood dips in Brazilian cohorts with 80% accuracy.
Predicting a mood dip based on gut bacteria, walk me through the mechanism there.
It's analyzing the production of neurotransmitter precursors. The AI identifies that a drop in sleep quality, combined with critically low levels of a bacteria called Coprococcus, means the body isn't synthesizing enough serotonin precursors. Predicting and averting a depressive episode or a severe inflammatory flare before it even begins is a far more profound use of AI than just reacting to a shadow on an X-ray.
That is a compelling argument, but have you considered that intercepting acute crises is definitively more impactful on a population level?
Impactful how?
Well, predicting a mood dip is a great luxury, and managing long-term dysbiosis is valuable. But if we're talking about the highest moral imperative for AI, we have to look at speed in life-or-death scenarios. Averting an immediate, catastrophic systemic failure is a tangible, measurable victory. That brings me to sepsis.
Okay, sepsis is a massive killer, yes.
Sepsis kills 11 million people annually, largely in low and middle income countries. It moves incredibly fast.
And it is notoriously difficult for clinicians to spot on a busy ward until the patient is already crashing.
Exactly, because the human brain struggles to correlate dozens of slight, concurrent physiological changes. A tiny drop in blood pressure, a slight spike in white blood cells, a fractional degree of fever over 12 hours. But recurrent neural networks thrive on that exact kind of sequential data.
Right, they excel at pattern recognition over time.
They don't just look at the current numbers, they look at the velocity of change. By analyzing electronic health records in a real time, Epic's AI predicts sepsis 6 hours before clinical onset. That algorithm is actively slashing ICU mortality by 20% in U.S. hospitals and is already being piloted in Nigerian wards.
6 hours is a massive clinical window.
It's the difference between life and death. Or look at Viz.ai stroke alerts. When a patient gets a diffusion MRI, the AI analyzes the asymmetries in the brain tissue and activates a thrombectomy alert in 90 seconds. It cuts the time to intervention by 50% across European stroke networks. You simply cannot wait for a bespoke health blueprint when a blood clot is actively starving the brain of oxygen.
I agree that speed is critical in those moments. But those acute crises don't happen in a vacuum. The underlying systemic inflammation that eventually leads to those acute vascular events is heavily modulated by the microbiome over decades.
Sure, but
However, I want to address the global deployment aspect you just brought up with the Nigerian wards. A very common misconception is that microbiome AI is some hyper-expensive luxury reserved for the wealthy.
which it often appears to be.
In reality, it is inherently global and democratizing. The Global Microbiome Conservancy is actively federating biological samples from 100 nations and open-sourcing the underlying TAI models via platforms like Hugging Face.
How does open sourcing a model actually translate to localized, on-the-ground care for someone in a rural setting, though?
By generating highly specific, culturally tailored interventions using local resources. TAI analyzes a local population's specific short-chain fatty acid producers to generate targeted dietary fiber prescriptions.
Like what, specifically?
For example, the AI identified that ragi, a highly accessible finger millet, is the optimal intervention for restoring metabolic health in specific Indian populations based on their unique microbial makeup. In another instance, TI-optimized taro ferments were used by Polynesian pilots to reverse their BMI by 10%. It is not a centralized, one-size-fits-all pharmaceutical pill. It is AI democratizing the deepest biological insights based on local, naturally accessible resources.
I'm sorry, but I just don't buy that.
Let me tell you why. The logistics of your approach are entirely disconnected from the reality of global medical infrastructure.
How so? The models are completely open source.
Yes, but the physical data collection isn't. The cost of next-generation sequencing has plummeted to about $50 a sample, sure. But that sequencing requires high-quality, intact DNA. How exactly do you transport a fecal sample from a remote village to a cloud-connected Thai sequencing lab when the cold chain logistics fail completely in places like the Congo's heat?
Well, you're relying on elaborate drone networks and continuous refrigeration that are highly susceptible to infrastructure collapse.
There are massive engineering efforts currently solving those exact cold chain dependencies with novel preservation buffers. We aren't just ignoring the heat.
But broad diagnostic AI is already functional at the point of care right now without needing a lab or a buffer. It is completely frictionless. Look at how Google's deep learning is deployed in Papua New Guinea. They aren't shipping biological samples across the globe. They're using mobile networks.
Exactly. A health worker takes a standard, cheap smartphone, attaches a $3 microscope lens over the camera, and the AI accurately flags Plasmodium parasites in a blood smear with 95% accuracy in seconds.
That is impressive, I'll admit.
Look at maternal health. Midwives in Afghanistan are using handheld ultrasounds equipped with AI overlays. The AI guides their hand and interprets complex fetal anomalies in real time, right there in the village, with no internet connection required. Peak Vision's fundus cameras detect diabetic retinopathy in Kenyan diabetics, finding 90% of cases in regions where blindness triples without intervention. This isn't waiting for a cold chain to be established. This is immediate, frictionless deployment that lives entirely on a microchip.
I hear you, but that exact frictionless deployment is precisely what makes broad diagnostic AI so perilous if we don't rigorously examine its epistemological hurdles.
Perilous? That's a strong word.
It is, but I will play fair. I will concede a limitation in the microbiome space first. We do face interpretation gaps where causality still eludes correlation. Just because a graph neural network finds a strong correlation between Klebsiella bacteria and liver fibrosis doesn't inherently prove the bacteria caused the liver damage.
Right. To put that simply for the audience, you mean using genetic anchors to mathematically prove that the bacteria actually caused the disease rather than just happening to be at the scene of the crime.
Precisely. We have to rely heavily on Mendelian randomization within the TAI probes. We have to untangle what is cause and what is merely effect. But I argue that the flaws in diagnostic AI are far more immediately dangerous because they are deployed at such massive automated scale.
I assume you are referring to the false positive rates?
I absolutely am. Let's look at the sepsis AI you praised just a few minutes ago. That system has a notorious 10% false positive rate in some deployments.
It's a conservative threshold to save lives.
But in an already overburdened hospital, sounding the alarm for sepsis when the patient doesn't actually have it is disastrous. It diverts critical nursing staff away from truly crashing patients. It burns through expensive broad-spectrum antibiotics, which ironically ruins the patient's microbiome, and it strains hospital resources to the breaking point.
No system is perfect out of the gate.
And worse, it operates as a black box. The algorithm flashes a red light and says, "This patient is crashing," but it cannot clearly articulate the biological mechanism of why. How can we trust a global diagnostic infrastructure that demands blind faith from its clinicians?
That is a highly valid critique. And early iterations of clinical AI absolutely suffered from the black box problem. But the engineering hasn't stood still. First, on the false positives, we now use ensemble thresholds.
Meaning multiple models voting?
Yes, this severely mitigates resource strain by requiring multiple distinct neural networks to mathematically agree before a severe alert is triggered. And the opacity issue, the black box, is actively being solved by SHAP values.
Explain how SHAP actually changes the clinician's interaction with the AI on the floor.
SHAP values essentially deconstruct the AI's decision-making process. It's the AI showing its math on the chalkboard so the doctor can verify it. If a CNN flags a lung CT for high cancer risk, the SHAP integration generates a visual heat map over the scan.
So it points out exactly what it's seeing.
Right. It highlights the exact pixels that influence the algorithm's math. It will generate a textual readout for the radiologist saying, Nodule speculation drove 70% of the risk calculation. It translates the black box mathematics back into the anatomical language the doctor actually understands and trusts.
That's definitely a necessary safeguard.
But if we are talking about epistemological hurdles, we have to acknowledge that the microbiome space has its own massive issues. It is currently drowning in commercial hype that vastly outpaces the rigorous science. We are seeing companies pushing gut reset miracles based on highly speculative beta diversity drifts. They got so bad that the industry required strict 2026 certification seals just to filter out the commercial charlatans.
The commercialization absolutely outpaced the clinical validation in the early days, yes. Which is exactly why those rigorous randomized controlled trials like the IBS study in Mumbai are now the gold standard.
But the foundational data itself was heavily skewed. The early microbiome AI was trained almost exclusively on Western, high-fat, North-centric populations.
That was a data collection issue, not a fundamental AI flaw.
But if you train a model strictly on a Western baseline, the algorithm simply breaks when applied to other populations. It's a fundamental math failure. It required massive post-hoc adversarial debiasing. Engineers literally had to pit neural networks against each other to mathematically force the system to recognize an Ethiopian teff-based microbiome as a healthy baseline, just so it wouldn't mistakenly flag healthy African guts as heavily dysbiotic.
That's fair.
Broad diagnostic AI, particularly with federated learning, trains borderlessly across diverse global data sets without requiring the physical transport of biological material, making it inherently more robust.
I completely agree that the data challenges are immense. Enforcing the models to debias was a necessary, painful evolutionary step for TAI. But as we synthesize our positions today, I maintain that mapping the gut's incredible complexity is where AI truly transforms human health at its root.
At its root, sure.
By utilizing tools like autoencoders and GNNs to decode the 100 trillion microbes within us, we aren't just creating a faster triage system for broken pipes. We are establishing a profound, predictive symbiosis between humans and our microbial ecosystems. It gives us the power to harmonize our internal biology with our environment, tweaking our precise nutritional inputs to preempt autoimmunity, mood disorders, and chronic disease long before they trigger a clinical alarm.
And I maintain that the ultimate trajectory of medical AI is in equalizing healthcare access right now. By replacing human error with immediate evidence-based precision, deploying CNNs and transformers across global diagnostic networks ensures that a patient in a rural clinic in Papua New Guinea receives the exact same standard of diagnostic accuracy as the patient in a premier research hospital in Boston.
It is a beautiful vision for equity.
By automating the detection of acute and chronic conditions, we avert immediate catastrophes and provide a scalable, democratized safety net that saves lives in real time.
It is worth noting, however, that despite our different applications, our perspectives fundamentally rely on the exact same underlying mechanisms. Whether we are parsing the gigabytes of a microbiome sequence or extracting the hierarchical features of a chest X-ray, the future relies on multimodal data fusion using graph neural networks and transformers.
Exactly. And both fields face identical algorithmic and engineering hurdles regarding data bias and privacy.
Right, like the microbiome doxing issue,
Exactly.
where a person's unique microbial fingerprint could be used to mathematically identify them from an anonymous database.
Or the GDPR data silos that fracture medical imaging datasets between Europe and Brazil. We have to solve the data governance issues before AI can reach its full 2040 potential.
Ultimately, to fully appreciate the future of medicine, we have to consider both the inner ecosystem and broad clinical data. The true synthesis of these technologies is actually already on the horizon. Models like MedPalm 3 are currently learning to integrate real-time MRI scans with the patient's personalized microbiome data and wearable inputs.
That's where it gets really exciting.
Right? It is simulating differentials that no human mind could ever hold at once, bridging the acute and the predictive. There is so much more to explore in how these systems will eventually talk to one another.
It brings us right back to the water system analogy you started with. We don't just need the advanced sensors predicting where the pipes will degrade over the next decade, and we don't just need the rapid response emergency teams for when they burst today.
We need both.
We need the central intelligence that connects the two. realizing that the chemistry of the water and the physical integrity of the pipe are ultimately the exact same system.
A system where eventually data democratizes our health destiny. Thank you for joining us for this analysis. We will see you next time on The Debate.